Okay, let's start now the second defense. Coming this afternoon. This is Sanaa Hobeichi. Your master title is indicated. You are supervised by Dr. Sumit Bakirana and co-supervised by Dr. Jennifer Dupont. Your advisory committee is composed of Dr. Nadim Hashim and Dr. Razwan Ahmed.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, everybody. First, I would like to welcome Professor Phillips, Dr. Hamda, Dr. Jennifer, and Dr. Suhul from ExxonMobil, and my colleagues, my family, my friends. I'm Sanaa Hobeichi, a master's in the environmental science program, a master's student. Today, I will be defending my master's project entitled An Integrated Approach to Benthic Habitat Classification of the Northeastern Qatar Marine Zone using remote sensing, geographic information system, and in situ measurements. In this presentation, I will give an overview of the work that I have been doing in the last 3 months. This is the outline of my presentation. I will start by introducing my project and stating my aims and objectives. Then I will go over some important concepts in my field of study. I will describe the methodology that I adopted in this project. I will present and comment on my results. And finally, I will summarize the outcomes of my project and suggest some future research that can be done in this field. Human development on the coasts of Qatar involve dredging and land reclamation for expanding residential areas, industries, and other projects such as the Pearl Qatar project, the Qatar-Bahrain-French Bridge project, oil and gas exploration and expansion project, and many other projects. And this all have a great impact on the coastal area and adjacent marine habitats, and can cause the destruction and alteration of marine habitats, and also habitat loss for many species. So why are we interested in benthic habitat classification? This is mainly because it provides a tool to facilitate efficient assessment of the state of the benthic cover, to detect changes to the habitat over time, and to potentially mitigate the impacts of human development on benthic habitats and communities. In fact, there is a gap in the available information on the benthic cover in the Qatari coastal marine zone. Previously, the characterization and classification of benthic cover in Qatar relied on field survey, but data collected from field survey provide information on scattered area of the benthic cover. In this project, in addition to the field data, I suggest and I propose to use high-resolution satellite imagery and also to apply proper image processing techniques in order to generate continuous data of the benthic cover. Actually, processing satellite imagery can use information on surveyed areas to generate information on unsurveyed areas. So benthic cover data captured via satellites and validated using field survey provides a cost-effective tool for benthic cover classification and can cover accessible and inaccessible areas. This project also uses GIS. GIS is a geographic information system, is a computer-based system designed mainly to analyze, manage, and present all types of geographical data. Actually, GIS was used in this project to store and manipulate benthic cover data, and also to produce maps that show benthic cover classification. The approach used in this project, which integrates remote sensing, GIS, and in situ measurements to map benthic cover, has not been adopted in Qatar before. Therefore, I believe that this project will generate interest in the development of future research. The aim of this project is to classify, map, and validate the benthic habitat at the northeastern part of Qatar Marine Zone by combining remote sensing techniques, GIS, and field data. In order to achieve this aim, the following objectives were considered: to correct remotely sensed data by applying pre-processing techniques, to apply image processing techniques in order to identify and produce benthic habitat classification, to validate the outcomes of the classification using field data, and finally to produce maps of benthic habitats. Now I will go over some important concepts about remote sensing. Actually, understanding these concepts aided the development of this project. And before I start working on this project, I didn't have any background about remote sensing and how it can be employed for benthic habitat classification. Sun emits electromagnetic radiation. Electromagnetic radiation is classified by wavelength, and the electromagnetic spectrum ranges from short wavelength, including gamma rays and X-rays, to longer wavelength, including microwaves and radio waves. Human eye only responds to the visible part of the spectrum, which lies between ultraviolet radiation and infrared. Sunlight that reaches the Earth's surface is composed of only a small portion of the electromagnetic spectrum, which ranges from ultraviolet to infrared. When the incident light coming from sun gets in contact with any substrate, absorption, reflection, or scattering can occur. In the case of seagrass, for example, most of the visible part of the spectrum is absorbed, except the green part, it's reflected from seagrass. And this is mainly due to the presence of the chlorophyll, and that's why the seagrass looks green. But for sand, more green and red wavelength is reflected. That's why it looks yellow to brown. In fact, different substrates differ in their sensitivity to various wavelengths. Optical sensors are sensitive to the reflected and emitted electromagnetic radiation. And if we compute the ratio radiance over irradiance, we can get the spectral reflectance or spectral signature of a substrate. Every substrate on the surface of the Earth is characterized by its spectral reflectance signature. Spectral signatures of the same substances is the same and different for different substances. So different substances can be distinguished from each other by their spectral characteristics, and that's how it's possible to distinguish different types of benthic cover using satellite imagery. To extract information about benthic cover using satellite, we need to remove the effect of the atmosphere and the effect of the water column, because the incident solar radiation received by benthic cover is influenced by the absorption and the scattering of the atmospheric components and the water column components as well. And also the radiation reaching the satellite at the top of atmosphere from benthic cover it's also influenced by the atmospheric components and water column components. In the atmosphere, scattering occurs when the incident radiation or the reflected radiation interacts with a cloud or airborne particulate matter, and this results in redirection of the incident radiation. But absorption occurs when the incident radiation or the reflected radiation hits a molecule of greenhouse gas, for example. Absorption and scattering reduce the intensity of the electromagnetic radiation. And that's why satellite imagery needs proper correction technique to remove the effect of the atmosphere. In the water, absorption occurs by the water molecule itself and by the chlorophyll usually present in algae and phytoplanktons. Scattering is mainly due to the presence of inorganic and organic particulate matter in suspension. Therefore, for benthic habitat classification and mapping, it's important to remove the influence of scattering and absorption from the water column. Another challenge in the marine remote sensing is the influence of the depth. The reflectance of the same substrate, such as seagrass, for example, changes with depth. Similarly, the reflectance of one substrate at one depth could be very similar to the reflectance of another substrate at a different depth. Therefore, for benthic habitat classification and mapping, it's important to remove the influence of water depth, scattering, and absorption. The intensity of the electromagnetic radiation detected by the sensor depends also on illumination geometry, which is related to the configuration, sun position, and observation geometry. The illumination geometry interferes in the data acquired by the sensors, which is stored as digital numbers. This means that satellite imagery needs to undergo an absolute radiometric calibration in order to convert the digital numbers to top of atmosphere radiance. The top of atmosphere radiance is the spectral radiance incoming toward the satellite at the satellite altitude. This project uses imagery from WorldView 2 satellite. WorldView 2 was launched by Digital Globe in October 2009. It has passive sensors that can detect the reflected energy when the source of energy is sun only. It orbits the Earth at an orbital altitude of 770 kilometers. WorldView 2 has an orbit period of about 100 minutes, and on average, it can revisit any point on the globe in 1.1 days. WorldView 2 is able to capture about 1 million square kilometers per day. It has a high spectral resolution sensor with 8 multispectral bands that range from the visible to near infrared. And also it has a high spatial resolution of about 1.8 meters in multispectral mode and 46 centimeters in panchromatic mode. So WorldView 2 has 1 panchromatic band and 8 multispectral bands that range from the visible to near infrared, from 400 nanometer to 1040 nanometer. And it can recognize 5 bands in the visible region: the coastal band, blue band, green band, yellow band, and red band. WorldView 2 is characterized by its 4 new bands, which are the coastal, the yellow, the red edge, and the near-infrared 2 band. In this section, I will describe the methodology that I adopted to achieve the objectives of my project. The study area is a strip section of the northeastern Qatari coastline, stretching from the north of Ras Laffan to the south of Al Ruwais. This is approximately a 35-kilometer stretch of coastline, and the total area covers 235 square kilometers, with water depth ranging from 0 to 11 meters. The study area is relatively undisturbed by human activities compared to the rest of the eastern coastline that includes the major industrial cities. And actually, mapping and monitoring the benthic habitats of undisturbed area is needed for a better protection of the benthic habitat and also for preservation of their related ecosystem. This project uses field data from the Ecological Baseline Survey carried out by the Environmental Studies Center ESC at Qatar University in conjunction with ExxonMobil Research Qatar EMRQ. The study area was divided into 10 transects from the south to the north, running from the land to the sea. Transects were spaced at 3.5 kilometers, and along those transects there was a total of 44 stations. Stations were surveyed at 250 meters, 1 kilometer, 2.5 kilometer, 5 kilometer, and sometimes 7 kilometers from the shorelines. And the field survey was done in the period March-April 2010. 3 types of benthic cover have been detected by the field survey: seagrass, which includes seagrass, meadows, and seaweeds; algae, which consists of macroalgae beds, and the most encountered macroalgae are brown; coral, represented by live corals; and in the area where there is no biological cover, the bottom type was sand or sometimes sand with dead coral. The project incorporated 12 WorldView 2 images, small images called tiles. some of the tiles were adjacent, and some of them were overlapping. Those images, when assembled, they cover the area of studies. Images were taken on April 2010, and actually, working with small size images allow software packages such as ENVI, IDL, and GIS to import and process the images. To meet the objectives of the project, 4 classes should be extracted from the image: seagrass, algae, coral, and sand, as explained in the previous slide. The first phase in the applied method was pre-processing the worldview 2 tiles. The land area was masked out from all the tiles that contain land surface. Then absolute radiometric correction was performed on the imagery to remove the effect of illumination geometry. An atmospheric correction model was then implemented to compensate for both atmospheric absorption and scattering. Seamless mosaicing was then applied to bind the tiles of images in one single image. And a water column correction program was developed and applied to remove the effect of the water column. Then for benthic cover classification, the field data showing the benthic cover identified at the 44 stations was imported as GIS layer. Training data from field survey was fed to a classifier to separate the different classes of benthic cover, and then ground truth from field survey data was used to assess the accuracy of the classification outcomes. And finally, the maps for benthic cover classification were produced. In addition to GIS, 2 software packages were used: ENVI 5.1 and IDL. ENVI, Environment for Visualizing Images, is a software designed to process and analyze satellite imagery. ENVI package includes a number of scientific algorithms for image processing. IDL, Interactive Data Language, is a programming language that can be used in ENVI environment. It's used to develop functions and procedures for pre-processing and processing satellite imagery. The land area was masked out from all the tiles to improve the contrast in digital numbers for non-land areas. Unwanted pixels were covered by polygons and then masked out to exclude them from the image processing. For radiometric correction, ENVI has a utility special for worldview 2 images. This utility uses information in the metadata file that's usually provided with each satellite image. It converts the digital number acquired by the sensor to top of atmosphere radiance images. And then, flash atmospheric correction module was applied to remove the effect of the atmospheric absorption and scattering, and to convert the top of atmosphere radiance into a meaningful measure of reflectance at the Earth's surface. Actually, FLASH is an algorithm that has a tropical atmospheric model and urban aerosol model for image correction. Seamless mosaicing was then applied to bind the tiles of reflectance images in one single composite image that covers the area of study. The real challenge was with the water column correction. Actually, there are very few packages for water column correction, but none is in ENVI. And the fact that there are not enough depth value available and no in situ measurements for spectral reflections of the benthic habitats, this made the choice of the water column correction technique very limited. The only available method was developed by Dr. Lysinga, and it consists of generating a depth invariant index image. And I had to program a module using IDL that can generate a depth invariant index image from my reflectance images. Depth invariant index method, like I will explain briefly about this method. This method consists of selecting a pair of 2 bands and plot the 2 bands one versus the other and draw the line of best fit for the plotted area or for the plotted data. The y-intercept of the line of best fit is the depth invariant index. Briefly, and without going into technical details, Depth invariant index distinguishes between bottom types by assigning an index for each homogeneous bottom type. So, from the surface reflectance image, depth invariant index images were generated, but it wasn't only one single index image generated. 48 different combinations of band pairs were used to generate the depth invariant index image. Each of the depth invariant index image was displayed in pseudo-color in order to increase the level of discrimination of different classes within the image. The visual interpretation of pseudo-color image showed that some band pairs have high potential to separate different classes. 4 band pairs showed this high potential. The red edge blue band pair, the green-yellow band pair, the green near infrared 2 band pair, and the blue-green band pair. Therefore, those 4 index images were selected to undergo supervised classification. Out of 44 station data, a random set of 22 station data was used as training data to perform supervised classification, and the remaining 22 station data was used for accuracy assessment and for the calculation of confusion matrix. Supervised classification, what it does is that it assigns every pixel in the image to a particular benthic class based on the training data fed to the classifier. The algorithm implemented for supervised classification is maximum likelihood classification. In this section, I will present and comment on my results. As I just mentioned, maximum likelihood classification algorithm produced a new pseudo-color image where each class is assigned a different color. The accuracy assessment of the classification outcomes was very low for the index image with the band pair blue-green. It was only 40.91%. Almost same results for the index image with band pair green near infrared 2. It was 45.45%. A little bit higher for the classification outcome. The classification outcome was a little bit higher for the index image with band pair red edge blue. It was about 63.34%, and relatively high for the band pair green yellow. It was 81.8%. The accuracy assessment of the classification results showed that the band pair that achieved the highest accuracy was green-yellow, with an overall accuracy of 81.8%. Hence, the band pair green-yellow was found to be the most appropriate band pair in Worldview 2 to discriminate between the different types of benthic habitats. And this conclusion helps validate many research done in this field. Then the index image with band ratio green-yellow, as it has shown the highest accuracy in reflection, the benthic cover classification, a confusion matrix was calculated for the outcome of this classification. Out of 7 ground truth regions of interest for algae, 5 were correctly allocated by the classifier to algae, 1 was allocated by mistake to sand, and 1 to coral. There was only 1 ground truth region of interest for seagrass, but it was allocated to coral. There were 2 ground truth regions for coral, 1 was correctly allocated for coral, and 1 was confused with sand. There were 12 regions of interest for sand, and all of them were correctly allocated to sand. Among the errors committed by the classifier, 66.67% were due to confusion with coral, and 14.29% were due to confusion with sand. And 28.57% of the regions of interest belonging with algae were allocated to another class, and 50% of ground truth for corals were allocated to another class. Now, user accuracy is calculated from the commission error, so it's the complement of the commission error, and the producer accuracy is the complement of the omission error. So we can see that for algae, the producer accuracy was 71.43% and user accuracy 100%. The seagrass, the accuracy was null for producer and user. For coral, the producer accuracy was 50% and 33.33% for the user accuracy. And for sand, the producer accuracy was 100% and 85.71% for the user accuracy. So we can see that the user and producer accuracies were high for algae and sand, whereas for coral classification, the user accuracy was low and the producer accuracy was average. This is probably due to two main reasons. When corals bleach or become stressed, they start losing their pigmentation and they change their spectral profile. And also some live coral species have spectral signatures that are similar to that of seagrass or algae. We cannot judge the user and producer accuracy for seagrass due to insufficient ground truth data belonging to seagrass class. There was only one ground truth data for accuracy assessment. The classification of the benthic cover can never be 100% accurate due to the fact that different types of benthic cover can overlap, creating confusion in the benthic cover classification. One limitation was the lack of field data. Out of 44 station data, a set of 22 station data was used as training data for maximum likelihood classification, and the remaining 22 station data were incorporated for accuracy assessment. This means that more reference points dispersed along the entire area of study at all depth and for all types of cover could improve the classification results and allow more accuracy assessment. Another limitation was the lack of in situ spectral measurements of the benthic features and the lack of bathymetric data. This made the choice of water column correction methodology very limited. However, it was fine for this project because it was still possible to discriminate between the target classes. This is the last section of my presentation. In this section, I will summarize the outcomes of my project and suggest some future research that can be done in this field. In this project, high-resolution WorldView 2 data was corrected for atmospheric and water column effects to classify and map benthic cover in the northeastern part of Qatar marine zone. Depth invariant bottom indices were calculated and formed the basis of this classification. Training data and ground truth data from field survey were incorporated to implement the supervised classification and accuracy assessment. The band pair green-yellow was found to be the most appropriate band pair in WorldView 2 to discriminate between the different types of benthic habitats. This project has produced a benthic habitat cover map for the northeastern part of Qatar marine zone. This map can be used as a standalone product to yield useful baseline information to the government stakeholders and researchers. Processing high-resolution satellite imagery supported with field data can be used to classify and map the benthic cover of the coastal marine zone. And this can generate valuable information of accessible and inaccessible areas for environmental monitoring, planning, and for scientific studies. The approach adopted in this project, which is in the integration of remote sensing, GIS, and in situ measurement in studying benthic cover, has not been adopted in Qatar before. And there are several interesting research ideas for future work, such as to monitor the changes in benthic cover over time, to develop a model for atmospheric correction that is aligned with the atmospheric composition in Qatar, and to incorporate more in-situ measurement to distinguish more features on benthic cover with a higher level of accuracy. I want to thank all the people that gave me the opportunity to do this project at Qatar University and at ExxonMobil, Dr. Samir, Dr. Nabil, and Dr. Andrew. And also my sincere thanks are for my supervisor, Dr. Sumit, and to Dr. Jennifer for their ongoing support, and also the very helpful advice of my advisory committee. And I'm also very grateful for ExxonMobil Research for providing me with the satellite imagery and for inviting me to attend a training presented by one of their remote sensing experts. And also thank you for ExxonMobil for the very friendly team. Thank you.
Thank you, Sanaa, for this very nice oral presentation, for very good work. And here I would like to thank again ExxonMobil Research Qatar, Dr. Jennifer, as we did this morning with Dr. Suhoor, and all the team, in the frame of the thesis of this morning, thesis of Naima, and this project, which is very useful for stakeholders and for policies makers or something like that in Qatar. So thank you very much. It's really a very interesting work. Now the question. Sorry.
Thank you.
Okay. Thank you. So okay, well, let's start with Dr. Yusri.
I have a loud voice, so I'm such a Thank you, Dr. Thank you, Sanaa, so much. This is really interesting study, but I have some questions, not only one. First, you talked about 44 stations, right? You collected in situ samples?
Yeah, actually, I didn't do the collection of the field survey. The field survey was already done by the Environmental Studies Center with incorporation with the ExxonMobil Research Qatar, and it was done in 2010. So even if there's some missing data, now I couldn't do anything. I had to work with the available data and proceed.
Also, you have no idea about what are the stations and the
No.
species or actually organisms that were collected at each station?
Actually, I know that they collected lots of things in the sediment, the different species there, but for my project, with the satellite imagery, actually we can map covers. We can't really recognize or discriminate between the different species there.
So what about the sand cover? You mentioned that these are algae, seagrass, corals, or sand.
Yep.
My information, because I'm working heavily in the northeast, and I collect samples of sediments as well. So most of the stations have mud. Have you tried to collect samples from the sediments and classify them if they are sand, mud? Because mud sometimes is dark and might provide different reflectance of light. So this might add to the misclassifications that you talked about or inaccuracy you talked about. So I would suggest in the next studies to collect samples of sediments and classify them to see if this is contributing to the. Also, you talked about coral is stressed, and this might be a cause for misclassification. So again, I asked you if you've seen samples and you could look at them to see if there are any bleaching of corals, but you just answered that you didn't look at them, right?
Yeah, actually my part was only trying to find or trying to produce a map that shows the different classes or the different types of benthic cover at that area. But the field data was given to me, and I didn't see the actual data.
Thank you so much.
You're welcome.
Thank you, Sanaa. I enjoyed your presentation. It was great. I have two questions. First question, the sample collection was only carried out during March and April 2010. Do you think this is, considering the changes of, although we don't have many seasons, but we do have some changes, considering those environmental factors, do you think this is sufficient?
Well, actually, when we want to use field data and satellite data, the perfect thing that can happen is to collect the data, the field data, at the same moment of capturing the image. That's the best situation. So the data has to be very, very aligned with the time of the imagery because of the atmospheric changes and the water column changes. So, like, you can't. Maybe some research do it, but for example, you can't collect the data in January and use a satellite image in April.
Yeah, I understand, but the samples could have been collected, let's say in the winter time, and then maybe spring and summer and the fall,
yeah.
And images also could have been taken at the same
Yes.
time to kind of correlate those. And my second question is, did you consider any of those environmental factors? Because many of the plants, seagrass you concentrated on, depend on many of the environmental factors, such as temperature.
Yeah, like, just to re-answer your first question, what you mentioned, that we can make several field surveys and use several images, satellite image, and we can see the changes over time. And that's what I suggest for future research. But with the available data for only one season, let's say, or for only the period March, April, that was what I can only generate one map.
But can't you do prediction?
Well, maybe we can do, but this will, after maybe studying for a long period, then I can reach a model. But I can't do a prediction only from one set of field data. That was the first question. For the second question, you mentioned that the environmental, well, I know that I wasn't really happy with using an algorithm, a universal algorithm, which is FLASH in this case, that does correction, the atmospheric correction. That's why also I suggested that we can do our own, with IDL, we can make a program to make our own module for atmospheric correction, where we can allow entering different parameters. So, for example, we can, depending on on the time and on the environmental situation, we can enter our parameters and do a better correction. You're welcome.
Thank you, Sanaa, for the really interesting talk. I've got a couple of questions about, I think, if I understood you correctly, you were talking about correction for depth and saying there were depth influences. Are those influences linear, or are they, how do they work? Is it
Actually,
within a certain distance of the surface, is it fine, and then it gets increasingly more difficult, or?
yeah. Now, regarding the depth, the radiation will attenuate with depth. Now, if we take very clear water, where there's no sediment, very, very clear water, for example, the near-infrared, it only reaches up to 5 to 6 meters. So there are some bands that we cannot use at a certain depth, and I'm sure that with the turbidity that we have, we cannot use the near-infrared, and many bands we cannot use them because, okay, I know that we have shallow water from 0 to 11, but we can't use all the bands due to the attenuation. Now, I mentioned depth, but I also used an algorithm which is depth invariant index. Like, it's an algorithm that it doesn't depend on the depth. It says that the ratio of attenuation of the different bands will be equal. That's what I relied on. So the line of best fit that I showed in the depth invariant index, from this line of best fit, we can generate two things: the depth invariant index, which is the y-intercept, and the attenuation coefficient. So no matter how was the depth or how the depth is changing, but the bands are attenuating in a ratio, respecting a ratio. So,
okay, that's really helpful. So where you get a heavier influence of depth or a greater degree of turbidity and therefore an issue there in terms of accuracy. Might that explain your accuracy models on your bands if they are expressing, perhaps your green-yellow is expressing in optimal depths and for clearer water zones than maybe one of your other bandings?
Yeah, actually what happens in the water is that the shorter wavelength, like blue and coastal blue, they are more scattered. And the longer wavelength, like red, they are more absorbed. So the bands in between green-yellow are like the best used in the marine satellite, in the processing of marines, like images in the coastal marine zone.
Okay, that's great, thanks. And my last question really is, if you've got a model now that you could use for future data, are there old data that you can plot backwards with? Are there old satellite data that you could enter into your model?
No, not the raw data, because the raw data are affected also with the illumination geometry. So first we have to remove this illumination geometry, which is related to the position of the satellite and the substrate or the cover that I want to map, and the sun position. So first I have to take in consideration that different places in my area of study are receiving different amount of light. So, and this will affect my results. So first, I have to convert the digital numbers, which are the raw data acquired by the satellite, to top of atmosphere radiance, which is the radiance received by the satellite, but with removing this illumination thing. So once I have the radiance values, like I can do the atmospheric correction if I'm only working in the terrestrial area, and then I can also add the water column correction if I'm working in the marine zone.
Okay, thanks very much.
Yeah.
That was excellent presentation, and I don't know nothing about remote sensing, but the way you explained it really, voice is not on?
No.
Can you hear me though? Thank you. I was just saying that the way you okay.
But I can hear, don't worry.
So the way you explained it, really you took me through it, and it seems that I have some idea what remote sensing is all about. Just one question. To my knowledge, there's a lot of mangroves in that area that you were studying, but you didn't really mention anything about the mangroves.
Yeah, actually, the mangroves were considered more with the terrestrial area, and they were also masked out. I know that there are also mangroves in the marine zone, but for this study, they were not interested with the mangroves classification. It was only the benthic cover classification. But I think, as you mentioned, it's very important to map also the mangroves.
Thank you. Well done.
Thank you.
Hey, may I ask a question? I'm not a marine biologist, so I may be asking really silly questions. But are those 4 habitat types, coral, grass, sand,
Microalgae?
yeah, algae, are those habitats exclusive enough to be treated as independent, let's say, vegetation or habitat? Because if there are any positive correlations, sometimes just separating those habitats as classified as a kind of independent category may not be biologically very meaningful.
Yeah, thank you for this question. And actually, we had a long debate about this question. It all depends on what's the aim of this project. The aim of this project might only be, for example, mapping corals and non-corals, mapping, let's say, seagrass and non-seagrass, mapping unconsolidated cover and consolidated cover, mapping, it depends on what the project wants. So when I was given the data, that was the question. We want you to map these 4 classes based on the field survey that we got. But maybe for the same imagery, we can do the same study, or we can use the same techniques in order to do another map, which maps, as you said, maybe corals and seagrass, macroalgae, sand, and maybe other things that are there. But with the field data that I had, I only have also these 4 classes. So it all depends on what do you want to do? What do you want to plan? So the field data was collected only to map these 4 classes. So that's why I did that.
Thank you.
Just one thing to Dr. Novel's question actually is a very good question. I think what Sanaa used, what we call hard classifier actually. Hard classification, when you force each pixel basically to take one role, there is an alternative way where we use what we call soft classification actually, where in the 4 types in each pixel you know the membership of each class in that pixel. That will give you an idea what's the best for certain things you are interested in, and that might address the point you raised actually.
Yeah,
and I'm willing to discuss that with you.
Thank you, Dr. Latia.
May I ask one more question? Okay. We have actually a big tide range between high tide and low tide here in the Qatari coastal water. And really, I'm not familiar with remote sensing, but during the low tide, I walk 2 kilometers to reach the water during the low tide. So will this impact the image and classification by any means?
Yeah, of course, if like, for example, the image was taken in the high tide, there will be a cover of water over the, like, you will have more water. This means that you need a water column correction for this area.
And do you have like timing for the image that as a time?
Yeah, in the method. Well, in the metadata file that's provided with the image, we have the exact time. Now, usually they take the images around like 9 to 10 in the morning, at 9 or 10 in the morning. So, like at that time, we can know what was covered and what was not covered by water.
Last question. Okay. So, thank you very much. I understand very well that you're working on the industrial area. It's your area, actually. But please, in the future, I recommend ExxonMobil to give some attention to the seagrasses. Actually, the true area of seagrass and the Salwa Gulf, is enriched in. And we want to know the situation of these seagrasses actually, because this seagrasses is correlated with the sea cows, Sea cows now, from my knowledge, in 1960s, I think, sea cows was maybe 2000s, I think, 12,000 individuals in our Qatari water. Now the count may be with hundreds, So I assume that the seagrass now in the Salwa area, or Salwa Gulf, is multi-dimensional. So if the company ExxonMobil can make some attention to this and may take or use your magnificent work to cover this area, that will be very, very good. Thank you very much.
Yeah.
So let me just really quickly say, so it's a great suggestion. And as Sanaa knows, seagrass, differentiating the seagrass and detecting the changes over a season is actually very easy to do with remote sensing. And we've acquired imagery for Gulf of Salwa and the WellView 2 with the WellView 2. And we've also just initiated a project with Qatar University on the dugong.
This area?
On the sea
This area? This
it's
area?
going to be that, yes, pretty much all around Qatar where they show up. So I'm happy to
Please
talk.
give attention to this area.
Okay,
Yes,
yeah, good.
Salwa Gulf, yeah.
But exactly, it's something that's on our minds, exactly. Thank you.
Okay, thank you very much again, Sanaa. And thank you all for joining us in this event, Master Defenses. Just to remind you that tomorrow we start at 8 with the 2 Master Defenses. In the similar room, 216, C216, in the female campus in the department. Okay. Thank you very much.